Good morning and welcome back. Today we're going to be starting our lesson on linearity and continuity of graphs. Today's goal is to determine whether functions are continuous, discrete, or neither, and to determine whether a function or functions are either linear or nonlinear. All right, discrete and continuous. Before we get to that, let's remember what we have learned about so far. First, we learned about relations. And from that, we were able to take mathematical relations and categorize them two ways. They are either a non-function or a function. From here, we have functions break into continuous, discrete, or neither. So, jumping on ahead, we have discrete functions. Discrete functions are probably the easiest one to identify. There are points that are not connected. This is literally just dots. So as we can see on our graph, it is just a bunch of dots. The domain of this is going to be an individual set of values. So if we take a quick look, those will be the x values from least to greatest. So we have -4, -1, 3, 4, 7. Remember, domain is x. Then for our range, since this is just a bunch of points or a bunch of dots, visually it's just going to be dots, we have our set of individual values, which would be a collection of the y values from least to greatest. So for the y values, we have -2, -1, 3, 4, and 5. After discrete function, the next is continuous. Continuous functions usually have arrows indicating they have continued direction. Points are connected to form a line or curve, and it's not just any type of line. It has to be a straight line. All lines are straight, but unfortunately not everyone keeps that mathematical definition in their head. By definition, a line must be straight. Now, for figuring out domain and range, what you really have to think about is the direction of the arrows. So when it comes to the x direction, this part is still, we see it's gaining distance in the x direction. So this one is going this way. As x increases, we get to greater and greater x values, and there's really no limitation to it. Because of that, the domain of this is all real numbers. That is to say, it's -infinity to infinity. Shorthand, r. Now, if we take a look in the y direction, which is up and down, these arrows are only pointing up. What that tells us is our y values have a bottom limit right here. This is y equals -5. So the range is going to start at -5 and go to infinity. So that's y greater than or equal to -5. Last one we have is neither discrete nor continuous. Some points are connected by a line or a curve, but it's not continuous everywhere. So for the one here, we get it has breaks. This is dots plus lines. The domain for this one, this one has a lower limit for both its x and y direction of -5. And we have a lower limit here. Well, I guess you'd say this is an upper limit because everything is less than. So for our domain, this is going to be -infinity to -5 plus 5 to infinity. And we have that gap in between. Ranges do the same thing. -infinity to -5 and 5 to infinity. The Bargain Book Barn sells young adult novels on a sliding scale. That is, the more books you buy, the cheaper they are. Let f of x model the store's prices for given quantities. If f of x is f of x discrete or continuous? Explain your reasoning. So they gave us a table, and we look at the graph. I see a bunch of dots, so my brain instantly goes to discrete. Use the table and context of this situation. The quantity and price corresponds to ordered pairs like 1 and 1.5, which can be graphed. Because books are not sold in fractional quantities, the number of books and their corresponding prices cannot be between the points given. So the points should not be connected and the function is discrete. The domain and range are going to be sets of individual values. Example 2. Determine whether f of x and g of x are continuous, discrete, or neither. Explain your reasoning. All right, taking a look at f of x, it's a curvy line, but there are no breaks in the line. We have arrows. Because f of x is graphed with a single curve, it is a continuous function. The domain and range are both all real numbers, and we know that because in the y direction we see we're still going down, and this one is going up. And in the x direction, this arrow is still gaining ground in positive x, and this one is still heading towards negative x. Now, over here, I see line segment and a point. So that should be neither. Because g of x has line sections, but is not a single line or curve, it is neither. The domain and range are intervals of numbers. Moving along. Check. Pause video. Check to determine whether f of x is discrete, continuous, or neither. All right, welcome back. Now, taking a look, I see just a bunch of dots, and by definition, just a bunch of dots is going to be discrete. Example 3. As a private investigator, Tia charges $25 per hour for any amount of time up to 8 hours and then a flat rate of $250 per day. Use the graph to determine if the function that models this situation is discrete, continuous, or neither. Is it discrete? The answer is no. This is not discrete because the graph is not entirely dots. We have a line segment there. Is it continuous? No, it is not continuous. This function cannot be drawn with a straight line or a curve. Is it neither? Yes. It is neither discrete or continuous. Plant circadian rhythms are cycles of behaviors that occur over 24 hours based on a day-night cycle. One aspect of a plant's circadian rhythm is the percentage of its flowers that are open or closed. F of x is represented by the curve. Is f of x discrete, continuous, or neither? Take a pause for a moment and figure it out. Since this is drawn with a single curve, this is going to be continuous. Next up, a linear function is a function that has a graph that is a line, and not just any line. We need to say it is a straight line. Again, by math rules, all lines are straight. A linear equation can be used to describe a linear function. And linear equations are often written in standard form. Now, I'm going to say this right now. A standard form of linear equations to me is the Barbie doll of the forms of linear equations. It's just meant to look pretty. And in order to graph it, unless you're able to easily graph the intercepts, you usually have to do some manipulation to it. And most people, if you showed them that, if they're not too educated in algebra, they won't even know if it's gaining ground, if it has positive slope or a negative slope. Now, I like to write these in the form of AX plus BY equals C. And we have this down here as well. I like using the colors for A, B, and C. Now, A must be positive, and whole numbers. No decimals or fractions. The standard form of linear equation, ax plus by equals c, where a is greater than 0, a and b are not both 0, and a, b, and c are integers with the greatest common factor of 1. So again, everything must be a whole number, so that means no decimals, no fractions. Examples, we have 2x plus 5y equals 7. A is 2, B is 5, and C is 7. In x equals -3, our A is 1, the B value is 0, removing y from the equation, and the C value is -3. This is where we start having integers of 0 remove things from equations. So technically speaking, we could write it 1x plus 0y equals -3. But this is a little bit clunky, so we just understand that 0 eliminates a value, so the y is gone, and that there's this invisible 1 in front of the x. A nonlinear function has a graph with a set of points that cannot all lie on the same line. An equation that represents a nonlinear function cannot be expressed in the form ax plus by equals c. The function values of a linear function change at a constant rate for every equivalent change in the x values. The change in the function values for a nonlinear equation will vary for equivalent changes in x. So what this means, if it's linear, you should be able to look at the jump between values. So maybe first data point to second data point and third data point to fourth data point. And they should have the same change between them. All right. We have the equation 4x squared minus quantity 2x squared plus 3x minus 5. And it asks if this is linear or nonlinear. So they give us steps over here to solve it, but we'll do a more complete version to the side. So we have evaluate our exponent to get 4x squared. Combining like terms, positive and negative 4x's cancel, leaving 0. We're left with 3x minus 5. So this becomes y equals 3x minus 5. This is slope-intercept form. We're going to learn more about equations in this form. Right now, we're getting to this form, and they're having us practice our algebra skills to convert them to standard. So from here, we now need to get this into standard form. So we're going to do this over here to the side. Now remember, standard form is ax plus by equals c. So we're going to start with y equals 3x minus 5. I see I have a constant on the left-hand side, but this x is not where it should be. I need to move it. So the first thing I'm going to do is subtract 3x from both sides. Cancel. Negative 3x y plus y, because it's a positive y, equals -5. All right, my x is now in the right position. My y is in the right position, and I have a -5 here. Now, I need to make this positive. So to make this positive, we're going to multiply this whole equation by -1. Negative 3x times -1 gives you 3x. Y times -1 is minus y. 5 times -1 gives us +5. All right, pause video for a sec, complete the check. Welcome back. Key to evaluating this one is to understand the square root of 9 is 3. That rewrites this second term as minus 3x squared. We have a positive and negative 3x squared, which will cancel that part out. We are left with negative y equals 17, which our spidey senses should tell us is y equals negative 17. This is linear. I totally butchered my spelling. Linear. There we go. We are now moving on to example 6. Selena kicks a soccer ball. The height of the ball after each second is recorded in the table. Is the function that models the height of the ball a linear or non-linear function? All right, now this is where we are going to start performing our check. So, linear means same value of I'll use this one. Of change in y over change in x throughout the whole table. Honestly, it's throughout the whole function. So what we're going to do is we're going to add a little column here, called not change in 5, change in x. And we check to see what the change is. So it's 0.5 from here to here, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. So what we see is at every step it increases 0.5. That is continuous. Same every time. All right, so this right here goes, well, so far it's looking pretty good. We have the same change happening at every time. Now, all we have to do is match that the y values will have the same change every single time. And why this matters is every one of these fractions, when we do our comparison, we need to compare 2 of these. The change in y is going to be the same in both of 0.5 and 0.5. Now, my first change in the y value for our change in y's, we have a positive 26. After that, it goes up 18, then it goes up 10. So already the jumps here are not the same. If we were to take this first one and the second one, well, we can see that this isn't the same. Once you have a counter example that shows that these two values aren't true, so that means this jump here, because it's both, it says this is a 0.5 jump, and this jump here, which is also a 0.5 jump, should be the same. All right, next example. Not example, this is our final check. Pause video and determine if these two are linear or non-linear. All right, let's break this down. So what we are looking for is the changes. So our change in x column over here is going to be +4, +1, +2, +1, +4. All right. Now this one is a little sporadic, but let's make our 5. 1, 2, 3, 4, 5. And our change in x's are 4, 1, 2, 1, 4. Change in y's, we have 12, 3, 6, 3, 12. Okay. 12, 3, 6, 3, 12. Hey, take a look. Each one of these fractions. 3 equals 3 equals 3 equals 3 equals 3. So even though the jumps aren't the same, what we see is the fraction of their change, the change in y over the change in x, is the same. So this one is linear. Now, over here, let's check out our change in x's. We have 1, 1, 1, 1, 1. All right, so every change is the same. All we have to do is verify that the changes in y's will be the same as well. So we have a -1, a -7, oh no, -19, we can stop. A jump of 1 had a change of -1, then a jump of 1 had a change of -7. This is nonlinear. And that is because if we take our change in y over change in x, -1 over 1 is not equal to -7 over 1. And that's the notes. Thank you so much. Have a wonderful day.